Let us look at an example of transportation model with a maximization objective. Now, the transportation model technique is essentially a minimization technique where we are trying to minimize the cost of shipping. However, problems involving maximization objective can also be solved using the transportation model. So let's see how we can use transportation model for a maximization objective. A company manufacturing air coolers has plants at Mumbai, Kolkata and Kanpur. Supplies are made to 3 showrooms situated at Ranchi, Delhi and Lucknow. So showroom can in other words be called as stores. So there are 3 stores at Ranchi, Delhi and Lucknow. Each manufacturing plant has capacity of 200 units per month. The monthly requirements of showrooms are 150, 300 and 150 numbers respectively. Due to the difference in raw material cost and transportation cost, the profit per unit is different for each showroom as given to us. Now, a point to be noted here is that we have been given profit per unit of moving the material from Mumbai to Ranchi, Mumbai to Delhi, Mumbai to Lucknow and so on. Now that is because this is a maximization problem. However, for the minimization problems, we generally have the cost per unit. So profit is to be increased, so maximization, and cost is to be decreased, so cost is related to minimization objective. Now what this table depicts is that if 1 unit of air cooler is sold through the Ranchi showroom and if it has been shipped from the Mumbai plant, then the profit per unit is 290 rupees. Similarly, if 1 unit is sold through the Ranchi showroom and has been shipped from the Kolkata plant, then the profit per unit is 250 rupees. And if it is again sold at Ranchi showroom and it has been shipped from the Kanpur plant, then the profit per unit is 350 rupees. Similarly, if it has been sold at the Delhi showroom and has been shipped from Mumbai plant, then the profit per unit is 280 rupees and so on. So now we have to find out which showroom should receive the material from which plant in order to maximize the profit. Now let's understand this example in more detail. So there are 3 plants, one at Mumbai, one at Kolkata and one at Kanpur. So let's say this is plant number 1. And this plant has a capacity of 200 units per month. So capacity is 200 per month. Now the next plant is in Kolkata. So let's say this is the second plant, P2, and this has the same capacity because all the 3 plants have the same capacity, 200 units per month. So capacity is 200 per month. And the third plant is in Kanpur. So let's place the plant here. This is P3 and this also has the same capacity, so capacity is 200 per month. Now this company has 3 showrooms, one at Ranchi, the other one at Delhi and the third in Lucknow. So let's say the Ranchi one is here. Let's say this is R for Ranchi and this has a demand of 150 units. per month. The second one is in Delhi, so this is D with a demand of 300 units per month. And the third one is in Lucknow with a demand of 150 units per month. Now, if 1 unit of air cooler is sold at the Ranchi showroom and is shipped from the Mumbai plant, then the profit is 290 rupees. So if we ship the material from plant 1, that is Mumbai, to the Ranchi showroom, the profit is 290 rupees per unit. And if we ship from Mumbai to Delhi and sell it at Delhi, the profit is 280 rupees. So at Delhi, the profit is 280 rupees per unit. And at Lucknow, 300 rupees per unit. Similarly, for Kolkata, if we ship the material to Ranchi, the profit is 250 rupees per unit. So Kolkata is P2 and Ranchi is this here. So profit is 250 rupees per unit. And if we sell the material at Delhi and it is shipped from Kolkata, then the profit is 270 rupees per unit. So to Delhi, this is 270 rupees per unit. And if we sell it in Lucknow while shipping from Kolkata, then the profit is 230 rupees per unit. So this is 230 rupees per unit, and so on. So now with this constraints and the options of profitability, we have to find out the shipping schedule in order to maximize the overall profit. So let's see how we can achieve that objective using the transportation model. Now the first step in solving the transportation model is formulation of a transportation table. In this step, we will express the supply from origin, requirements at destination, and the profit per unit in the form of a matrix. So let's create that table. On the left hand side, we'll place the plants P1, P2, P3. Let's say P1 is Mumbai, P2 is Kolkata, and P3 is Kanpur. On the extreme right, we'll place the capacities. Now it has been given that all the three plants have the same capacity, which is 200 units per month. So this is in units per month, and it is 200. On the top, we will place the showrooms. Let's say the showrooms are S1, S2, and S3, where S1 is Ranchi, S2 is Delhi, and S3 is Lucknow. And at the bottom, we'll place their demand. So S1 has a demand of 150. This is again units per month. S2 has a demand of 300 units per month, while S3 has a demand of 150 units per month. And in the middle, we'll place the profit in rupees per unit. So 290, 280, 300, 250, 270, 230, 350, 370, and 380. Now a check needs to be done to find out if the total of supply is equal to the total of demand. If the supply is equal to demand, then the problem is said to be balanced, and if not, a dummy origin or destination is added to balance the supply and demand. So here the total of supply capacity is 600 and the total of demand is also 600. So this is an example of balanced transportation problem. Now this problem has a maximization objective, and there are three ways to solve a maximization objective problem using the transportation model. The first two ways are essentially converting a maximization problem into a minimization problem. So let's look at these in detail. So the first option is to subtract each of the profit elements from the largest profit element. So let's understand this. Let's say there are 5 numbers, 1, 2, 5, 6, 9. This is A, B, C, D, E. Let's say we want to find out the maximum number or the maximum value. So we know that 9 is the greatest, so the maximum value is for E, which is 9. Now let's say we want to find the minimum value and still get the solution as E. How can we get that? So one of the options is, let's subtract all these numbers by 9. So 9 minus 1 is 8, 9 minus 2 is 7, 9 minus 5 is 4, 9 minus 6 is 3, and 9 minus 9 is 0. So when we did this, what happened is all these numbers reversed in their value. So the smallest value number, which was 1, became the largest value number, which is 8, and the largest value number, which is 9, became the smallest value number. So now again, we'll ask the question for these values, find out the minimum number, and again the answer will be E. So here it was maximization, and here it is minimization, and still we get the same answer. So that is what the option number 1 says. Subtract all the profit values from the largest profit value, and that will reverse the value of all these numbers, and then we can solve this problem using the minimization method. Now let's look at the second option. So let's take the same set again, and if we have the maximization objective, we want to find out the maximum number. The answer is E, which has 9 as the value, which is the maximum value in all these numbers. Now again, we want to convert this into minimization problem and at the same time get the answer as E. So if we multiply all these numbers by minus 1, then what will we get? We will get minus 1, minus 2, minus 5, minus 6, and minus 9. Now we know that if this is our axis, this is 0, 1, 2, 3, 4, 5, and minus 1, minus 2, minus 3, minus 4, and minus 5. So on the positive side, As the numbers increase, their value increases. And on the negative side, as the negative number increases, the value decreases. So minus 5 is smaller than minus 3. Similarly, minus 4 is smaller than minus 3. So here, now we are evaluating this set of numbers and we are trying to find out the minimum number. That is the minimization objective. So again, what is the answer? Answer is minus 9, which is again E. So the second solution option is to multiply each of these profit values with minus 1. That will reverse the value of the profit numbers, and then we can solve this problem using minimization method. Now the third solution option is to solve the problem as a maximization problem. Now how do we do that? So we'll use the same methods as used for the minimization objective problems. However, we'll just reverse the objective from minimization to maximization while solving the problem. So what does that mean? So while finding the basic initial feasible solution, in case of a minimization objective, we allocate to the cell with the lowest cost, and instead of that, in maximization objective, we will have to allocate to the cell with the highest profit value. So that will take care of the basic initial feasible solution. Now, instead of the solution being optimal when all the net change values are positive, the solution will be optimal when all the net change values are non-positive or less than equal to 0. Because what this means is that if the net change value is positive, then we can increase the profit by making allocation to that cell. So we can use any of these three methods to solve the maximization objective problem. Let's use the first method and see how we can solve this problem at hand. So in this first method, we have to subtract all these profit numbers from the maximum profit number, which is 380. So let's do that. So 380 minus 290 is 90. 380 minus 280 is 100. 380 minus 300 is 80. 380 minus 250 is 130. 380 minus 270 is 110. 380 minus 230 is 150. 380 minus 350 is 30. 380 minus 370 is 10. And 380 minus 380 is 0. So as you can see, the lowest number, which was 230, is now having the highest value of 150, and the highest number, which was 380, is now having the lowest value of 0. So we can now solve this with a minimization objective. So let me fill in the right values in the appropriate places so that we can proceed with solving this problem. So this is the transportation table that we have obtained after converting the maximization problem into a minimization problem. So now the next step is to find out the basic initial feasible solution, and let's use Vogel's approximation method to find that out. Now the first step in Vogel's approximation method is to calculate the difference between two minimum elements for each row and each column. So let's first do row wise and then we'll do column wise. So for the first row, the lowest is 80 and next lowest is 90. So the difference is 90 minus 80, which is 10. For the next row, the lowest is 110 and the next lowest is 130. So the difference is 130 minus 110, which is 20. For third row, the lowest is 0 and the next lowest is 10. So the difference is 10 minus 0, which is 10. Now let's do column wise. So for the first column, the lowest is 30 and the next lowest is 90. So 90 minus 30, which is 60. For the second column, the lowest is 10 and the next lowest is 100. So the difference is 100 minus 10, which is 90. And for the third column, the lowest is 0 and the next lowest is 80. So the difference is 80 minus 0, which is 80. Now the next step is to select the row or column with the largest difference. So the second column has the largest difference of 90. Now the next step is to allocate the maximum number of units to the square with the minimum cost in the selected row or column. So we have to select the square with the minimum cost, which is P3S2. Now since we are solving this example as a minimization objective now, we are trying to allocate the maximum to the square with the lowest cost. However, as per the third method for solving a maximization problem, at this stage, instead of choosing the cell with the lowest cost, you would choose the cell with the highest profit. Alright, so let's continue with the same minimization objective. So now we have to allocate the maximum that we can to this square P3S2. Now S2 has a demand of 300 units while P3 has a supply capacity of 200 units. So the maximum that can be allocated is 200 units. So with this allocation, the entire supply capacity of P3 has been exhausted, while the remaining demand for S2 is now 300 minus 200, which is 100. Now since the entire supply capacity of P3 has been exhausted, let's cross off the remaining boxes indicating that they are no longer available for allocation. Now let's redetermine the row and column differences. So for the first row, again 90 minus 80 is 10. For the second row, again 130 minus 110, which is 20. Third row we can skip as it is completely allocated. For the first column, 130 minus 90, which is 40. For the second column, 110 minus 100, which is 10. And for the third column, 150 minus 80, which is 70. Now let's find out the row or column with the largest difference. So that is the third column. Now let's allocate the maximum to the square with the lowest cost in this column, which is P1S3. Now P1 has a supply capacity of 200 units while S3 has a demand of 150 units. So the maximum we can allocate here is 150. Now with this allocation, the remaining supply capacity at P1 is 50 units, while the remaining demand at S3 is now 0. Now since with this allocation the entire demand of S3 has been met, let's cross off the remaining boxes for this showroom, indicating that they are no longer required to be allocated. So now let's redetermine the row and column differences. So for the first row, difference is 100 minus 90, which is 10. For second row, 130 minus 110, which is 20. You can skip the third row. For the first column, 130 minus 90, which is 40. For the second column, 110 minus 100, which is 10. And we can skip the third column. Now we have to find out the row or column with the largest difference, which is the first column. So let's try to allocate the maximum to the square with the lowest cost in this column, which is P1S1. Now P1 has a supply capacity of 50 while S1 has a demand of 150. So even though S1 has a demand of 150, P1 can only supply 50 units. So the maximum we can allocate is 50. Now with this allocation, the supply capacity remaining at P1 becomes 0, while the remaining demand at S1 is now 150 minus 50, which is 100. Now since the entire supply capacity at P1 has been exhausted, let's cross off the remaining boxes indicating that they are no longer available for allocation. So now we have only two boxes remaining which are not yet allocated or crossed off. Let's choose the one with the lower value of cost, which is P2 S2. And let's try to allocate the maximum that we can to this square. So P2 has a supply capacity of 200 units while S2 has a demand of 100 units. So the maximum we can allocate is 100 units here. So with this allocation, the entire demand at S2 has been met, and the supply capacity remaining at P2 is now 200 minus 100, which is 100. Now the next square is P2 S1. S1 has a demand of 100 units while P2 has a supply capacity of 100 units. So we can easily allocate 100 units here. So the demand remaining at S1 is now 0, while the remaining supply capacity at P2 is also 0. So now with this we have allocated all the supply and demand. So this becomes our basic initial feasible solution. So at this point we would find out the total cost in case of a minimization problem. However, since this is a maximization problem, we should find out the total profit. So we can find out the total profit by multiplying these allocations with the profit per unit for these allocations. So from P1 to S1, the profit is 290. So 290 multiplied by the number of units, which is 50, plus from P1 to S3, the profit is 300 multiplied by the number of units, which is 150, plus from P2 to S1, 250 multiplied by 100, plus from P2 to S2, 270 multiplied by 100, plus from P3 to S2, 370 multiplied by 200. So let me put my calculator here. So 290 multiplied by 50 plus 300 multiplied by 150 plus 250 multiplied by 100 plus 270 multiplied by 100 plus 370 multiplied by 200. So 185,500. 185,500 rupees. This is the total profit obtained after the basic initial feasible solution. So at this point we have a basic initial feasible solution, which means that this solution will give us a shipping route without violating the supply and demand constraints that we were given. However, we don't know if this profit is the maximum that can be obtained with these constraints given to us. So in order to now find out if this solution is optimal or not, we have to perform an optimality test. However, before we move forward with the optimality test, we have to first find out if this solution is acceptable enough to proceed with the optimality test. So let's perform the acceptability test first on this basic initial feasible solution. So let me rewrite the basic initial feasible solution and we'll proceed with the acceptability test then. Now for the acceptability test, the first condition is that the number of allocations should be equal to m plus n minus 1, where m is the number of rows and n is the number of columns. So here m is 3 and n is also 3. So 3 plus 3 is 6, minus 1 is 5. Now let's count the number of allocations. So we have 1, 2, 3, 4 and 5. So the number of allocations is equal to m plus n minus 1. So this condition has been met. Now the next condition is that these allocations should be in independent positions. Now a simple rule of thumb for allocations to be in independent positions is that it is impossible to travel from any allocation back to itself by a series of horizontal and vertical jumps from one occupied cell to another without a direct reversal of route. Or in other words, you can't create a closed loop for any of these cells with an allocation. So if you observe, you'll find that all these allocations are independent. That is, you can't create a closed loop for any of these allocations. So this condition is also met. So now we can proceed with the optimality test. Let's use the stepping stone method to perform the optimality test. Now basically in this optimality test, we have to evaluate each and every square which does not have an allocation to find out if an allocation were made to that square, will it improve the overall solution that we had obtained. So the first step in the stepping stone method is to select water squares row by row. So the water squares are the squares without any allocation. So the water squares in our case are P1S2, P2S3, P3S1 and P3S3. Now the next step is to establish a closed path using rectilinear motion, that is moving horizontally and vertically only, starting from the selected water square via the stone squares and then back to the same water square. Now a right angle turn is made only at the stone square, even though the path may skip over stone and water squares. So let's try to create the closed loops for each of these water squares. The first water square is P1S2. So for P1S2, the closed loop can be P1S1, P2S1, P2S2 and then back to P1S2. So P1S2 to P1S1 to P2S1 to P2S2 and then back to P1S2. Now next step is to assign alternate plus and minus sign on the closed path, starting with a plus sign on the water square. So this is plus, minus, plus and minus. Now the next step is to calculate the net cost change for the path. Now the net cost change is obtained by summing up the unit cost of each cell. So P1S2 has a unit cost of 100 minus P1S1 is 90 plus P2S1 is 130 minus P2S2 is 110. So 100 minus 90 is 10, 10 plus 130 is 140 and 140 minus 110 is 30. Let's move to the next water square, which is P2S3. So for P2S3, the closed loop can be P2S3 to P1S3 to P1S1 to P2S1 and then back to P2S3. So P2S3 to P1S3 to P1S1 to P2S1 and then back to P2S3. Now assigning alternate plus minus sign, so plus minus plus minus, and then we have to calculate the net cost change. So P2S3 has 150, P1S3 has 80, P1S1 has 90, P2S1 has 130. So 150 minus 80 is 70, 70 plus 90 is 160, 160 minus 130 is 30. Now the next water square is P3S1. So let's form the closed loop for P3S1. The closed loop can be P3S1 to P2S1 to P2S2 to P3S2 and then back to P3S1. So P3S1 to P2S1 to P2S2 to P3S2 and then back to P3S1, assigning alternate plus minus, so minus plus minus, and then assigning the cost. So P3S1 is 30 minus P2S1 is 130 plus P2S2 is 110 minus P3S2 is 0. So 30 minus 130 is minus 100. Minus 100 plus 110 is 10. 10 minus 0 is 10. Now the last water square, which is P3S3, let's form the closed loop. So the closed loop for P3S3 will be P3S3 to P1S3 to P1S1 to P2S1 to P2S2 to P3S2 and then back to P3S3. So P3S3 to P1S3 to P1S1 to P2S1 to P2S2 to P3S2 and then back to P3S3. Now assigning alternate plus minus signs, so minus plus minus plus minus, and then assigning the cost value. So P3S3 is 0 minus 80 plus 90 minus 130 plus 110 minus 10. So 0 minus 80 is minus 80 plus 90 is 10. 10 minus 130 is minus 120. Minus 120 plus 110 is minus 10. Minus 10 minus 10 is minus 20. Now the next step is to evaluate the solution for optimality by observing the sign of the net cost change. So the net cost change values for us is plus 30, plus 30, plus 10 and minus 20. Now the presence of a negative sign indicates that a cost reduction can be made by making an allocation to this square, and it also indicates that this solution is not the optimal solution and can be improved further. So the square which can provide us improvement is P3S3, which is this square. So now let's iterate towards optimality and find out an improved solution.
So now that we have identified P3S3 as the water square with the negative net cost change value, let me draw the closed loop that we had identified for this water square. So this is the closed loop that we had identified for P3S3. Now let's assign alternate plus minus sign, starting with a plus sign for the selected water square. So plus, minus, plus, minus, plus, minus. Now the next step is to subtract the smallest of the figures from each square at the negative sign on the closed path and add it to each square at the positive sign on the path. So the squares with the negative sign have an allocation of 150, 100 and 200. So the smallest of the figures is 100. So let's subtract 100 and add 100. So here we'll add 100. Here we'll subtract 100. So this becomes 50. Here we'll add 100. So this becomes 150. Here we'll subtract 100. So this becomes 0. Here we'll add 100. So this becomes 200. Here we'll subtract 100. So this becomes 100. So this becomes our new improved solution after the first iteration. So let me clean this up. So this is the new solution that we have obtained. So let's first calculate the total profit that we have achieved with this improved solution. Now the total profit will be the multiplication of the profit obtained by selling 1 unit multiplied by the number of units allocated. So here the number of units allocated are the ones in circle. However, the other numbers in these squares do not reflect the profit because we had subtracted it from the maximum number. So I'll use the profit numbers for these squares and multiply them with these allocations. So we get 290 multiplied by 150 plus 300 multiplied by 50 plus 270 multiplied by 200 plus 370 multiplied by 100 plus 380 multiplied by 100. So let's calculate this. Let me pull my calculator. So 290 multiplied by 150 plus 300 multiplied by 50 plus 270 multiplied by 200 plus 370 multiplied by 100 plus 380 multiplied by 100. So the value we get is 187,500 rupees. So the profit that we had obtained after the basic initial feasible solution was 185,500 rupees. So definitely we have been able to increase the profit by 2000 rupees. Now we have to find out if this is the optimal solution or if this solution can be further improved. So we have to perform an optimality test on this solution. However, before we proceed with the optimality test, we have to find out if it is acceptable to proceed with the optimality test on this solution. So there are two conditions to perform the acceptability test. The first condition is that the number of allocations should be equal to m plus n minus 1. M is the number of rows and n is the number of columns. So we have 3 rows and 3 columns. So this becomes 3 plus 3, 6 minus 1 is 5. Now let's calculate the number of allocations. So we have 1, 2, 3, 4 and 5. So this condition is met. Now the second condition is that the allocations should be in independent positions, which means that we should not be able to formulate a closed loop for any of these allocations. So if you observe, all these allocations are in independent positions. So this condition is also met. So now we can proceed with the optimality test, and we'll use the stepping stone method to perform the optimality test. So in the stepping stone method, we have to proceed row by row and select the water squares, that is the squares without any allocations. So P1 S2, P2 S1, P2 S3, P3 S1 are the water squares. The next step is to establish a closed path using rectilinear motions, starting from the selected water square via stone squares and then back to the same water square. So for the first water square, which is P1S2, the closed path would be P1S2 to P3S2 to P3S3 to P1S3 and then back to P1S2. So P1S2 to P3S2 to P3S3 to P1S3 and then back to P1S2. Next we have to assign alternate plus minus sign on the closed path, starting with a plus sign on the water square. So this is plus, minus, plus, minus. Next we have to calculate the net cost change for the path. The net cost change is obtained by summing up the unit cost of each cell. So let's fill in the unit cost. So P1S2 has a unit cost of 100 minus P3S2 has a unit cost of 10 plus 0 minus 80. So 100 minus 10 is 90, 90 minus 80 is 10. Now the next step is to evaluate the solution for optimality by observing the sign of the net cost change. So here all the net cost change values are positive, which means that there is no water square which can help us reduce any cost further, and which in turn means that we have reached the optimal solution. So this is our optimal solution and the total profit is 187,500 rupees. So here basically the allocation is from P1 to S1 we'll be shipping 150 units, P1 to S3 will be shipping 50 units, P2 to S2 will be shipping 200 units, P3 to S2 will be shipping 100 units, and from P3 to S3 another 100 units.